Ever since the discovery of the bizarre behavior of quantum systems, we've been forced to reckon with a seemingly uncomfortable truth. For whatever reason, it appears that what we perceive of as reality, where objects definitively exist in definite locations with intrinsic properties that can always be measured exactly, isn't exactly an accurate description of what is real. Instead, many of those physical properties themselves cannot be fundamentally determined by any means. As long as you don't measure or interact with your quantum system, what we interpret as reality exists in an indeterminate state. We can only speak of the properties it possesses and the outcomes of any potential measurements in a statistical, probabilistic sense. Each measurement always returns one and only one answer, but predicting exactly what physical state we're going to measure ahead of time cannot be done via any known method. But is that a fundamental limitation of nature, where there exists an inherent indeterminism until a measurement is made or a quantum interaction occurs? Or could there be a hidden reality that's completely predictable, understandable, and deterministic that underlies what we see? It's a fascinating possibility, one that was preferred by no less a titanic figure than Albert Einstein, but one that no physicist, including Einstein, has ever concocted a satisfactory answer to. Interestingly, back in the 1960s, a theorem was proved, known as the Kochen-Specker theorem, that asserted that no hidden variables absolutely cannot exist within quantum mechanics. But here in 2025, does that line of reasoning still hold up? It turns out that reality is a complicated thing, especially when it comes to quantum phenomena. Let's start with the most famous example of quantum indeterminism to investigate, the Heisenberg uncertainty principle. In the classical macroscopic world, there's no such thing as what quantum physicists know as the measurement problem. Classically, you can take any object that you like, a jet, a car, a tennis ball, a pebble, or even a mote of dust, and you can not only measure any of its properties that you want to, but based on the laws of physics that we know, we can extrapolate what those properties will be arbitrarily far into the future. All of Newton's, Einstein's, and Maxwell's equations are fully deterministic. If you begin with the locations and motions of every particle in your system or even in your entire universe, the laws of physics can tell you precisely where they will be and how they'll be moving at any point in the future. The only uncertainties we'll have are set by the limits of the equipment we're using to take our measurements, and as we decrease those measurement uncertainties, our predictive power becomes ever greater. However, once we begin considering objects in the quantum world, this is no longer true. There is an inherent uncertainty to how well, simultaneously, you can know a wide variety of properties together. If you try to measure, for example, a particle's position and momentum, energy and lifetime, spin in any two perpendicular directions, or its angular position and angular momentum, you'll find that there's a limit to how well you can simultaneously know both quantities. According to the Heisenberg uncertainty principle, the product of the uncertainty on both of those properties can be no smaller than some fundamental value, which is proportional to Planck's constant. In fact, the instant you measure one such quantity to a very fine precision, the uncertainty in the other, complementary one will spontaneously increase so that the product is always greater than a specific value. One illustration of this, shown above, is the Stern-Gerlach experiment. Quantum particles like electrons, protons, and atomic nuclei have an angular momentum inherent to them, something we call quantum spin, even though nothing is actually physically spinning about these particles. In the simplest case, these particles have a spin of 1/2, which can be oriented either positively, plus 1/2, or negatively, 1/2, in whatever direction you measure it. Now, here's where it gets bizarre. Let's say we shoot these particles. In the original version of the experiment, they used silver atoms through a magnetic field oriented in a certain direction. Half of the particles will get deflected in one direction, for the spin equal sign plus 1/2 case, and half will get deflected in the other, corresponding to the spin equal sign, 1/2 case. If we then pass these particles through another Stern-Gerlach apparatus oriented the same way, there will be no further splitting. The 1/2 particles and the 1/2 particles will remember which way they split. But if we instead pass them through a magnetic field oriented perpendicular to the first set of magnets, they'll split once again in the positive and negative directions, as though there was still this uncertainty in which ones were plus 1/2 and which ones were 1/2 in this new direction. And now, if we go back to the original direction and apply yet another magnetic field, they'll go back to splitting in the positive and negative directions again. Somehow, measuring their spins in the perpendicular direction didn't just determine those spins, but somehow destroyed any information that we previously knew or determined about the original splitting direction. This is definitely not intuitive and is a puzzle that practically calls out for some way to make sense of it. The way we traditionally handle this is to recognize that there's an inherent indeterminism to the quantum world that can never be completely eliminated. Whenever anyone attempts to exactly determine a property of a particle, such as the spin of that particle in one particular dimension, the corresponding uncertainty in the perpendicular dimensions must become infinitely large to compensate. Otherwise, Heisenberg's inequality would be violated. There's no cheating when it comes to the uncertainty principle. You can only obtain meaningful knowledge about the actual outcome of your system through measurements. However, there has long been an alternative proposal to attempt to explain what's going on: the idea of hidden variables. In a hidden variables scenario, the universe would really be deterministic in a sense. All quanta would actually have intrinsic properties that would enable us to predict precisely where they'd end up and what the outcome of any quantum experiment would be in advance. The only problem is that some of those hypothetical variables, the ones that govern the behavior of this system, cannot be measured by us here in our present reality. In other words, those variables are assumed to exist but are hidden from our ability to measure them. In principle, if we could measure these variables, we'd understand that what we perceive as an indeterminate behavior that we observe merely reflects our own ignorance of the variables that determine what's truly going on. If we could find, identify, and understand the behavior of these hidden variables that truly underlie reality, the quantum universe wouldn't appear so mysterious after all, and would instead reveal an underlying, completely deterministic reality. The way I've always conceived of hidden variables is to imagine the universe, down at the quantum scales, to have some set of dynamics that govern it, but that we do not understand. However, assume that even though we can't or don't understand what those dynamics are, we are able to directly observe the effects that those dynamics cause. It's like imagining our reality made up of grains of sand, where each individual grain appears to fluctuate, jitter, and move around randomly, similar to the Brownian motion of particles that Einstein discussed in one of his miracle year papers back in 1905. However, we can imagine that this jitter is caused by some sort of mechanism that's simply invisible to us. For grains of sand, we can imagine that they're hooked up to a vibrating plate that lies underneath them, but that the plate is completely unobservable, hidden from our reality. On the other hand, we can easily observe the grains of sand that lie atop the plate. If all you could see were those grains of sand, it would look to you as though each individual grain were vibrating with a certain amount of inherent randomness to it. Even large-scale patterns or correlations that you could observe might even exist between disparate grains of sand, but you couldn't predict the behavior of any one grain in particular. However, because you cannot observe, measure, or even detect the vibrating plate beneath the grains, you cannot know the full set of dynamics that govern this physical system. Your knowledge is the thing that's incomplete, and what appears to be random, the motion of sand grains, actually has an underlying explanation, albeit one that cannot be fully understood by someone who cannot observe such a plate. It's a fun idea to explore, but like all things in our physical universe, we must always confront our ideas with measurements, experiments, and observations that can be made from within our material universe. One such experiment, in the opinion of many physicists, the most important experiment for illustrating the behavior of quantum physics, is the double-slit experiment. When you take even a single quantum particle and fire it at a double slit, you can measure on a background screen where that particle lands. If you do this over time, hundreds, thousands, or even millions of times, you'll eventually be able to see what the pattern that emerges looks like. Here's where it gets weird though. If you don't measure which of the two slits the particle goes through, you get an interference pattern. Spots where the particle is very likely to land, and spots in between where the particle is very unlikely to land. Even if you send these particles through one at a time, the interference effect still persists, as though each particle were interfering with itself. But if you do measure which slit each particle goes through, such as with a photon counter, a flag, or via any other mechanism, that interference pattern doesn't show up. Instead, you just see two clumps, one corresponding to the particles that went through the first slit, and the other corresponding to those that went through the second. Many variations of the double-slit experiment have been performed, and while they reveal an enormous amount of information about the type of quantum weirdness that exists within our universe, they cannot reveal or exclude the presence of hidden variables. One of the greatest physicists of the 20th century was John Wheeler. Wheeler was thinking about this observed quantum weirdness, and in particular about the fact that these quanta sometimes behave as particles and sometimes as waves. Because of this, he began to devise experiments that attempted to catch these quanta in the act of switching their behaviors, acting like waves when we expect particle-like behavior and vice versa. Perhaps the most illustrative of these experiments is shown above, passing a photon through a beam splitter and into an interferometer, one with two possible configurations, open and closed. Interferometers work by sending light in two different directions and then recombining them at the end, producing an interference pattern dependent on the difference in the path lengths, or the light travel time, between the two routes. Wheeler conceived of two possible configurations for such an experiment. If the configuration is open, as shown at the top of the above figure, you'll simply detect the two photons individually and won't get a recombined interference pattern, as there will be no beam splitter to recombine the beams in the final location. If the configuration is closed, as shown at the bottom of the above figure, then interference will occur, and you'll see the wave-like effects on the screen. What Wheeler wanted to know is if these photons knew how they'd have to behave in advance. He'd start the experiment in one configuration, and then, right before the photons arrived at the end of the experiment, would either open or close or not the apparatus at the end, either inserting or removing the final beam splitter even while the photons themselves were already in transit. If the light knew what it was going to do, you'd be able to catch it in the act of being a wave or particle, even when you switched the final outcome. In all cases, however, the quanta did exactly what you'd expect they would have done had they known what the final configuration was going to be all along.